Hello everyone. Today we will study parametric equations. First of all, let me introduce what are parametric equations. A group of functions with the same variables is called parametric equations. Let me show you an example first. For example, if I let x equal to f of t, which is t squared plus t, and let y equal to g of t, which is 2t minus 1, then we have two functions with the same variable t. In this example here, x and y, they are called parametric equations. S equal to f of t and y equal to g of t. Together, these two equations together, they are called parametric equations. And also for both equations, t is the common variable, so t is called a parameter of these parametric equations. The parameter t, the variable t is called a parameter of the parametric equations. Note, in this example here, if we consider the set of ordered pairs x and y are points in the xy plane, then for every t values in the domain, there's a corresponding point in the xy plane. There is a corresponding point in the xy plane. For example, when t is 0, the ordered pair xy equal to, if I plug in 0 here, x is 0. If I plug in 0 here, y is -1. When t is 1, if I plug in 1 for x, I get 2. If I plug in 1 for y, I get 1. So we can see that for every t value, there's a point in the xy plane. Since every t value in the xy plane represents a point, then the set of all t values together will form a group of points. And in general, this group of points will form a curve, and this curve is called a parametric curve. Next, let me introduce parametric curve. The set of points x and y for all t values in the domain in general form a curve in the xy plane. And this curve is called the parametric curve. Now let me show you how the parametric curve looks like. In the previous example, x equal to t squared plus t, and y equal to 2t minus 1. If we make table for t and x and y, we will have a set of points. Let's pick some value for t. We can pick some positive value, negative value for t. Let's pick -2, -1, 0, 1, and 2. Then for each t value, we find a value for x and y. When t is -2, we plug -2 here for t and find x. I get +2. When t is -2, we plug -2 here. 2 times -2 minus 1, I get -5. When t is -1, I plug -1 here. X is 0. If I plug in -1 here, y is -3. If I plug in 0, I get 0. If I plug in 0, I get -1. When I plug in 1, I get 2. When I plug in 1 here, I get 1. When I plug in 2, 2 squared plus 2 is 6. When I plug in 2 here, 2 times 2 minus 1 is 3. So for each t value, we have a point. Then plot each point in the xy plane. Plot each point on the xy plane. When t is -2, the point is 2, -5. S is 2, y is -5. That's the first point when t is -2. When t is -1, the point is 0, -3. When s is 0, y is -3. It's here. That's the point when t is -1. When t is 0, the point is 0, -1. The point is here. 0, -1. When t is 1, the point is 2, 1. That means s is 2, y is 1. That's the point when t is +1. When t is +2, the point is 6, 3. Means x is 6, y is 3. 1, 2, 3, 4, 5, 6. X is 6, y is 3. 1, 2, 3. The point is here. That's the point when t equal to +2. Then connect this point, we can make a curve. Connect this point using smooth curves, we can make a curve here. Connect this point using smooth curves. This curve is called a parametric curve. This curve here is called a parametric curve. And the direction, from the direction of the curve, we can see that as t increase, the curve, the object on the curve move this way. As t increase, the object on the curve move this way. That's called the direction of the curve. So that's the direction as t increase. That's the direction as t increase. That's a complete graph for these parametric equations. Next, let me show you more graphs about parametric equations. Graph each of the following parametric equations. Consider this example: x equal to 2 to the power of t, y equal to 2 to the power of negative 2 to the power of negative t, where t is between negative 3 and positive 3. Here, if I specify the t value, that's the domain of t values. That's the domain of t values. If the problem specifies the t value, that's the domain of t values. So in order to sketch a graph, let's make a table first. Make a table for t and s and y. Here, since t varies from negative 3 to 3, we can pick t to be negative 3, negative 2, negative 1, 0, 1, 2, and 3. Then for each t value, find the corresponding x and y values. When t is negative 3, 2 raised to negative 3 is 1 over a. When t is negative 3, 2 raised to negative 3 is positive a. If I plug in negative 2, 2 raised to negative 2 is 1 over 4. 2 raised to negative 2 is 4. If I plug in negative 1, 2 raised to negative 1 is a half. 2 raised to negative 1 is 2. If I plug in 0, 2 to the power 0 is 0. It's 1. 2 to the power 0 is 1. If I plug in 0 here, 2 to the power 0 is 1. If I plug in 1, 2 to the power 1 is 2. 2 to the power of negative 1 is a half. 2 to the power 2 is 4. 2 to the power of negative 2 is 1 over 4. If I plug in 3, 2 to the power 3 is 8. 2 to the power of negative 3 is 1 over 8. Then connect this point, we can make a graph. Let's plot this point first. Let's plot this point first. First point, x is 1 over 8, y is 8, somewhere here. Second point, x is 1 over 4, y is 4, somewhere here. Third point, x is half, y is 2. And the fourth point, x is 1, y is 1, somewhere here. Next, x is 2, y is half, somewhere here. Next point, x is 4, y is 1 over 4. And the last point, x is a, y is 1 over a, somewhere here. Connect all these points, we can make a curve. And from the direction of the curve, we can see that as t increases, the point goes this way, the point shifts this way. As t increases. And since t varies from negative 3 to 3, those are the terminal points of the curve. Since t varies from negative 3 to 3, those are the terminal points of the curve. Next example, s equal to 2 cosine t, y equal to 2 sine t. Sketch a graph for this parametric equation. So let's make a table first. Choose some value for t and sy. Usually for trig functions, we pick t value to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. Pick the values in the first cycle. Pick values in the first cycle from 0 to 2 pi. If I plug in 0, cosine 0 is 1, 2 times 1 is 2. Sine 0 is 0. If I plug in pi over 2, cosine pi over 2 is 0. Sine pi over 2 is 1, 2 times 1 is 2. If I plug in pi, cosine pi is negative 1, negative 1 times 2 is negative 2. Sine pi is 0. If we plug in 3 pi over 2, cosine 3 pi over 2 is 0. Sine 3 pi over 2 is negative 1, negative 1 times 2 is negative 2. If we plug in 2 pi, cosine 2 pi is 1, 2 times 1 is 2. Sine 2 pi is 0, 2 times 0 is 0. So that's the points. Next, plug this point. When t is 0, we have point 2, 0. When t is pi over 2, we have point 0, 2. When t is pi, the point is negative 2, 0. When t is 3 pi over 2, the point is 0, negative 2. When t is 2 pi, the point is 2, 0. 2, 0, go back to here. So when t equals 2 pi, we go back to this point. Then connect this point using smooth curve. Connect this point using smooth curve. Connect this point using smooth curves. That's the graph. Then the direction as t increase. Direction as t increase, it goes this way. That's called counterclockwise. The direction is counterclockwise. So here we know that we can sketch graph by plotting points. By plotting point may be too complicated. Is there any easier way? Observe this example here. If I rewrite function y is 2 raised to negative t, it can be rewritten as 1 over 2 to the power t. And we know that 2 to the power t is x. 2 to the power t is x. So I can replace 2 to the power t with x. So this parametric equation can be written as y equal to 1 over x. And from the table, you can see that this is the initial point. When t equals to negative 3, that's the initial point. When t equals to 3, that's the end point. So it's y equal to 1 over x from 1 over a, comma a to point a, comma 1 over a. So this graph can be described using this function here. And graphing this function is much easier than plotting points. How about this example here? How can I write x and y together? How can I write x and y together? In this equation, if I solve this equation for t, then plugging t into the first equation, I can get an equation with only x and y. So I can solve for second equation for t, y equal to 2t minus 1. If I solve an equation for t, I have y plus 1 equal to 2t. So t equal to half of y plus 1. Then I can substitute t into the first equation. I have s equal to half of y plus 1 squared plus half of y plus 1. Then I can simplify the equation. I get 1 over 4 y squared plus 2y plus 1 plus half of y plus 1. Half of y plus half. Then simplify. I can distribute 1 over 4. I get 1 over 4 y squared plus half of y plus 1 over 4 plus half of y plus half. If I combine like terms, I have x equal to half of y squared plus y plus 3 over 4. And we see that this is a second degree function. This is a parabola. And this graph matches a parabola here. How about this equation here, this parametric equation here. How can we write x and y together? It doesn't look too easy. It doesn't look too easy. Here, think of this. What if I square both sides? What if I square both equations? If I square first equation, I can write x squared equal to 2 times cosine square of t. Y squared equal to 2 squared times sine square of t. Which means x squared over 4 equal to cosine square t. Y squared over 4 equal to sine square of t. We know that cosine square plus sine square is 1. Cosine square plus sine square is 1. So x squared over 4 plus y squared over 4 equal to 1. If I multiply both sides by 4, I get x squared plus y squared equal to 4. 4 is 2 squared. That's a circle of radius 2. That's a circle of radius 2. This equation matches this graph. And using this equation is much easier than using parametric equations. Using an equation with only x and y is much easier than using parametric equations. Same thing for this equation. Using an equation with only x and y is much easier than using parametric equations. Same thing for this one. So we know that if we try to graph a parametric equation by plotting points, it may be too much work. An easier way is we can try to eliminate perimeter t first and get an equation with only x and y. Then graphing this equation will be much easier than graphing the parametric equations. Next example. Graph the following parametric equations. By eliminating the perimeters first. First example, x equal to 3t minus 1, y equal to 2t plus 5, and t is between the interval from -2 to 4. T is from -2 to 4. We try to eliminate the perimeter first. That means we try to eliminate t first. So here, for these two equations, we can solve one of an equation for t, then substitute into the other equation. In the first equation, if I solve for t, I have x plus 1 equal to 3t. Then I can divide both sides by 3. I get 1/3 of x plus 1 equal to t. Then substitute this t into the second equation. I get y equal to 2 times 1/3 times x plus 1 plus 5. Distribute 2/3. I get 2/3 of x plus 2/3 plus 5. Y equal to 2 over 3x plus 17 over 3. And we know this is a linear equation. This is a linear equation. The graph of this equation is a straight line. If we try to graph a straight line, we need to find 2 points on the line. Once I find 2 points, I can fix a line. Now, how do we find 2 points for this line? When we try to find 2 points of a line, we can try to use the endpoints. We can try to use the endpoint here. So the initial point is t equal to -2. Endpoint is t equal to 4. When t equal to -2, x is -2 times 3 minus 1, which is -7. Y is 2 times -2 plus 5 is 1. When t equal to 4, we plug in 4 into the equation here. X is 3 times 4, that's 12. 12 minus 1 is 11. Y is 2 times 4 is 8. 8 plus 4 is 13. Then by plotting these two points, we can graph a line. First point, x is -7, y is 1. That's the first point when t equal to -2. That's the initial point. Second point is 11, 13. X is 11, y is 13. That's the point when t equal to 4. Then that's the initial point, that's the end point. Connect 2 points using a straight line. That's the graph of these parametric equations. And what's the direction as t increase? We know that's the initial point, that's the end point, so the direction must be this way. So that's the direction of the parametric equation. Next example, s equal to t squared plus 1, y equal to t to the power 4 plus 1. How can we eliminate t here? If I solve the first equation for t, I get s minus 1 equal to t squared. So t equal to plus or minus square root of s minus 1. That's too complicated. If I solve the second equation for t, I get y minus 1 equal to t to the power 4, which means t is plus or minus the 4 root of y minus 1, which is still complicated. So if we try to substitute this into the second equation, the answer may be too complicated. What can we do here? Let's observe this equation here. First equation contains t squared. Second equation contains t to the power 4. If I solve the first equation for t squared, I get s minus 1 equal to t squared. Then if I square both sides, I get t to the power 4 equal to x minus 1 squared. Second equation contains t to the power 4. I can substitute s minus 1 squared into the second equation. So second equation can be written as s minus 1 squared plus 1. I substitute s minus 1 squared for t to the power 4. And that's the equation with only x and y. Graphing this equation is easier than graphing these parametric equations. Now how do we graph this equation? This is a parabola, second degree equation. This is a parabola. This is parabola. Center at 1, 1. This is parabola, center at 1, 1. That's the vertex of the parabola. What's the y-intercept? What's the s-intercept? For the y-intercept, I plug in 0 for x. If I substitute 0 for x, I get 2. So the y-intercept is 2. And what's the s-intercept? If I let y be 0, I get x minus 1 squared equal to -1. And perfect square cannot be -1. There's no solution. So that means there are no s-intercepts. And since the leading term has positive coefficient, this parabola opens upward. So graphing this parabola is much easier than graphing these parametric equations. But now my question is, be very, very careful here. Is this graph correct? Is this graph correct? Let's observe this parametric equation first. X is t squared plus 1. We know that t squared is always greater or equal to 0. So t squared plus 1 must be greater or equal to 1. That means x must be greater or equal to 1. 1 is here. So x must be greater or equal to 1. We don't have this part. We don't have half of the parabola. We don't have the entire parabola here. So the graph is half of the parabola. Here y is also greater than 1. When s is greater than 1, it guarantees y is also greater than 1 here. We only have half of the parabola. Here y is also greater or equal to 1. And for this half piece here, y is also greater than or equal to 1. So this is the graph of these parametric equations. Now, how about the direction? what's the direction of the parametric equation as t increase? Let's plot some points. Here we can see the direction. Let's plot some points. When t is 0, we have x and y equal to 1, 1. When t is 0, we are here. How about when t is 1? When t is 1, we have two, 2. 1 squared plus 1 is 2. 1 to the power 4 plus 1 is also 2. So when t is 1, we are here. It looks like we are going this direction up. Now let's be very careful. Let's test some negative number first. Let's also test some negative number. What if t is negative 1? When t is negative 1, we have negative 1 squared plus 1, that's 2. Negative 1 to the power 4 is also 1. 1 plus 1 is 2. When t is negative 1, we are here again. Then what's the direction? Negative 1, 0, 1. When t is negative 1, we are here. When t is 0, we are here. When t is 1, we bounce back to this point. What's the direction? So it looks like when t is negative, the curve goes this way down. When t is negative, the curve goes this way down. Then when t hits 0, we reach the point 1, 1. When t becomes positive, it goes this way back. It bounces this way back. So the curve goes this way down first, then goes this way back. That's the direction in the parametric graph as t increases. Next example, s equal to 2 sine t, y equal to 3 cosine t. How can we eliminate t here? Here, both parametric equations contain sine and cosine functions. I can try to solve the equations for sine and cosine. Then use the identity cosine square of t plus sine square of t equal to 1. So for the first equation, if I divide both sides by 2, I get sine of t equal to s over 2. For the second equation, if I divide both sides by 3, I get cosine of t equal to y over 3. Then if I square both sides, I have sine square of t equal to s squared over 4. Cosine square of t equal to y squared over 9. Then we know that sine square of t plus cosine square of t equal to 1. We have s squared over 4 plus y squared over 9 equal to 1. This equation represents ellipse. For x-intercept, I set y equal to 0. If I plug in 0 for y, I get x squared over 4 equal to 1. That means x squared equal to 4. S equal to plus or minus 2. For y-intercept, I plug in 0 for x. So I get y squared over 9 equal to 1. That means y squared equal to 9. Y equal to plus or minus 3. So y-intercept is plus or minus 3. S-intercept is plus or minus 2. Connect the intercepts, we can make an ellipse. Now, how about the direction? What's the direction of this parametric curve as t increase? Let's test some points. For direction, let's test some points. When t equal to 0, what do we get? When t is 0, sine 0 is 0. Cosine 0 is 1. So the point is 0, 3. That's the point when t is 0. When t is pi over 2, what's x and y? When t is pi over 2, sine pi over 2 is 1. So I get 2. Cosine pi over 2 is 0. We get 0. So that's the point when t is pi over 2. How about pi? When t is pi, what's x and y? When t is pi, Sine pi is 0. Cosine pi is -1. So I get -3 here. That's the point when t equal to pi. So don't let the curve go this way. The curve moves clockwise as t increases. The curve moves clockwise as t increases. Next, we will study calculus with parametric equations. First of all, let me introduce the derivative of parametric equations. Let x equal to f of t and y equal to g of t be parametric equations. Where the functions f of t and g of t are both differentiable. Also, let y be a differentiable function of x. Let y be a differentiable function of x. Then, how do we find dy over dt? How do we find dy over dt? If we use chain rule here, dy over dt can be rewritten as dy over dx times dx over dt. That's chain rule. If you use chain rule here, dy over dt is the same as dy over dx equal to dx over dt. Now, if we solve this equation for dx over dt, if we solve this equation for dy over dx, then dy over dx can be written as dy over dt over dx over dt. If we solve this equation for dy over dx, then dy over dx equal to dy over dt over dx over dt. This is the derivative of parametric equations. This is the derivative of parametric equations. We use this formula to take derivative for parametric equations. Let's look at some simple examples here. Let s equal to t plus square root of t. Y equal to t minus square root of t. Assume they are parametric equations. Find dy over dx. So here we use the formula. Dy over dx equal to dy over dt over dx over dt. For dy over dt, I first put in function y here, take derivative with respect to t. I get 1 minus half of t raised to negative half. Then for dx over dt, in the function of x here, take derivative with respect to t. I get 1 plus half of t raised to negative half. If we simplify this answer here, I can multiply the top and the bottom by 2t raised to a half. Multiply top and bottom by 2t raised to a half. Because 2 will cancel half. T raised to half will cancel t raised to negative half. If I distribute, I get 2 square root of t minus 1. 2t raised to half times 1 is 2 square root of t. And when I multiply 2t to the half to the second term, 2 times half is 1. T to a half and t to negative half can cancel. For the bottom, we have 2 square root of t plus 1. So that's dy over dx. That's the derivative of these parametric equations. Next example. Let x equal to 2t to the power 3 plus 1. And y equal to t squared cosine t. Find dy over dx. Assume they are parametric equations. Find dy over dx. So for dy over dx, use the formula dy over dt over dx over dt. For dy over dt, I take derivative in function y with respect to t. Here I use product rule here. Here I use product rule. Derivative of the first times the second plus the first times derivative of the second. That's dy over dt. Then for dx over dt, take derivative with respect to t. I have 6t squared. That's the denominator. Then here, if I simplify, on the numerator, I can pull out t. If I pull out t, I have 2 cosine t minus t sine t over 6t squared. I can cancel one of the t from top and the bottom. So the answer is 2 cosine t minus t sine t over 6t. Next example. Let s equal to t squared minus 2t minus 3 and y equal to t cubed minus 2t squared. Find the equation of a tangent line at t equal to 2. For equation of a line, if we try to find equation of a line, we must know a point and a slope. So for equation of tangent line, also need to know a point and a slope at t equal to 2. Let's find a point first. When t equal to 2, s equal to 2 squared minus 2 times 2 minus 3, which is 3. Y equal to 2 to the power 3 minus 2t squared, which is 0. So 3 comma 0, that's the point when t equal to 2. Next, we need to find a slope when t equal to 2. To find a slope, we must find a derivative. The derivative represents the slope of tangent line. So let's find derivative first. dy over dx is dy over dt over dx over dt. For dy over dt, take derivative in function y with respect to t. I have 3t squared minus 4t. For dx over dt, in function x, take derivative with respect to t. I get 2t minus t. That's the derivative. Then for the slope of tangent line, we plug in the t value. Plug in the t value into the derivative. If I plug in 2 for t, I get 3 times 2 squared minus 4 times 2 over 2 times 2 minus 2. Numerator is 12 minus 8, which is 4. Denominator is 4 minus 2, which is 2. 4 over 2 is 2. So when t equal to 2, slope of tangent line is also 2. Then we can find equation of a line. Y minus y0 equals slope times x minus x0. That's the equation of a line, where m is the slope, x0, y0 is the point on the line. So that y minus 0, we have y minus 0 equal to 2 times x minus 3. Get y by itself, we have y equal to 2x minus 6. That's the equation of tangent line at t equal to 2. Next example, let s equal to t squared and y equal to t cubed. Find the equation of a tangent line at point 4, comma a. In order to find the equation of a tangent line, we must know a point on the line, and we need to know the slope of tangent line. Here we know a point on the line here. For slope of tangent line, we must compute the derivative, because derivative represents slope of tangent line. So let's compute derivative first. For derivative, dy over dx is dy over dt over dx over dt. Dy over dt is 3t squared. ds over dt is 2t. If I simplify this equation, I have 3t over 2. That's the derivative, which is the slope of tangent line. Then for slope of tangent line, we plug in a value. What should we plug in here? Since in this equation variable is t, we must plug in a t value. So in order to find the slope, we must find out what is the t value at this point, 4, a. So here, let's solve an equation for t. We have x equal to t squared. X coordinate is 4, so I write 4 equal to t squared. We have y equal to t cubed. Y coordinate is a, so I write a equal to t cubed. If we solve these two equations for t, in the first equation I get t equal to positive 2 and negative 2. In the second equation I get t equal to 2. The common solution is 2. The common solution is 2. That means when t equal to 2, the s and y coordinate is 4, a. When t is 2, the s and y coordinate is 4, a. So we know that at this point, 4, a, the t value is 2. So for the slope, I plug in 2 from the t value. Then plugging 2 into the derivative, I have 3 times 2 over 2, which is 3. So the slope of tangent line at this point, 4, a is 3. Then we know a point, we know the slope, we can find the equation of the tangent line. Equation of a line is y minus y0 equal to slope times x minus x0, which is y minus a equal to 3 times x minus 4. If we simplify the equation, we have y minus a equal to 3x minus 12, y equal to 3x minus 4. That's the equation of tangent line at this point, 4, a. Next example, let s equal to t squared, y equal to t cubed. Find the equation of the tangent line passing through the point 4, a. It looks very similar as the previous problem. Previous problem is asking for equation of tangent line at the point 4, a. And this problem is asking for equation of tangent line passing through the point 4, a. What's their difference? Be very, very careful. They are not the same thing. For example, that's the parametric curve. Assume that's the parametric curve. Assume that's the point 4, a. This line here is called the tangent line. The tangent to the curve at the point 4, a. This line here is called the tangent line. The tangent to the curve at the point 4, a. That's what we found in the previous problem. But for a tangent line passing through 4, a, there could be a different point. There could be another point. There could be another tangent line. This is another tangent line to the curve. This is another tangent line to the curve. It tangent to the curve at a different point by also passing through the point 4, a. So it could be multiple points passing through this point. It could be multiple tangent lines passing through this point. So let's first of all find out for what t values there's a tangent line passing through the point 4, a. So let's first of all find out for what t values there's a tangent line passing through this point 4, a. So let's find the slope first. Derivative represents slope of tangent line. Let's find the slope first. Derivative represents slope of tangent line. Let's find the slope first. The derivative dy over dx is dy over dt over dx over dt. dy over dt, take derivative of function y with respect to t, I get 3t squared. For ds over dt, take derivative of function x with respect to t, I get 2t. Simplify, I get 3t over 2. So that's the slope. That's the slope of tangent line. Now we know the equation of line is y minus y0 equal to the slope times x minus x0. So we know the point here is 4, a. In the tangent line, a point on the tangent line is 4, a. A point on the tangent line is 4, a. So x0, y0 here is y0 is a, x0 is 4. And y, I can substitute t cube. For all points on the curve, y is t cube. And for all points on the curve, x is t squared. Slope is the derivative. Derivative represents the slope of tangent line. So I plug in 3t over 2 for the slope. Then I can solve this equation for t. Then I can solve this equation for t. First of all, I can multiply both sides by 2, make it a little easier. Multiply both sides by 2. So I get 2 times t cubed minus a equal to 3t, t squared minus 4. Distribute 2, I get 2t cubed minus 16. Distribute 3t, I get 3t cubed minus 12t. Then combine like terms. I can move 2t cubed over. I get t cubed minus 12t plus 16 equal to 0. Then solve this equation for t. This is a third degree equation here. How do we solve for t? For a third degree equation, t cubed minus 12t plus 16 equal to 0. We first of all need to guess for an answer. We can use calculator to guess for answer. Here, by guessing, we know that when t equal to 2, t cubed minus 12t plus 16 equal to 2 cubed minus 12 times 2 plus 16, which is 8 minus 24 plus 16. That's 0. So by guessing, we know that 2 is a solution to this equation. So by guessing, we know that 2 is a solution to this equation. So to find the rest of the solution, I do long division. Take t cubed minus 12t plus 16. Do long division. Since t is equal to 2 is a solution, that means t minus 2 must be 0. So this must be a factor to this equation. So take this function, divide by t minus 2. T times t squared is t cubed. Then take t squared times t and negative 2. I get t cubed minus 2t squared. Then subtract. T cubed minus t cubed can cancel. 0 minus negative 2t squared is 2t squared. Bring the rest down. Next, we know t times 2t will be 2t squared. T times 2t will be 2t squared. Take 2t, multiply to both terms. I get 2t squared minus 4t. Then subtract. 2t squared minus 2t squared can cancel. 12t minus negative 4t. Negative 12t minus negative 4t is negative 8t. Bring 16 down. We know t times negative a is negative 8t. Take negative a, multiply to both terms. I get negative 8t plus 16. When we subtract, we get 0. If there's no remainder, that means this polynomial t cubed minus 12t plus 16 can be factored as t minus 2 times t squared plus 2t minus a. So for a third degree equation, we can try to guess for answer. Then do long division and find a factor form for this polynomial. So here, this polynomial t cubed minus 12t plus 16 can be factored as t minus 2 times t squared plus 2t minus a. Keep factoring, I get 0 equal to t minus 2 times t plus 4 times t minus 2. That's t minus 2 squared times t plus 4. Then if we solve this equation for t, I get t equal to 2 and t equal to negative 4. That means when t equals to 2 and t equal to negative 4, there's a tangent line passing through the point 4, comma a. Next, let's find the tangent line when t equal to 2 and negative 4. When t equal to 2, the slope is dy over dx. I plug in 2 for the t value. I get 3t over 2, which is 3 times 2 over 2 equal to 3. So that's the slope of tangent line. We know that 4, comma a is a point on the tangent line. I have y minus a equal to the slope times x minus 4. If I simplify, I have y minus a equal to 3x minus 12. So y equal to 3x minus 4. That's one tangent line passing through the point 4, comma a. This is the same as the previous tangent line. Next, when t equal to negative 4, the slope is 3 times negative 4 over 2. When t is negative 4, the slope is 3 times negative 4 over 2, which is negative 6. Then plug in. We know a point on the tangent line is 4, comma a. We have y minus a equal to negative 6 times x minus 4. Then simplify. You get y minus a equal to negative 6x plus 24. Y equal to negative 6x plus 32. That's another tangent line passing through the point 4, comma a. So in general, when we're looking for tangent line passing through a point, there are multiple answers. Next example, let s equal to t cubed minus 3t squared minus 9t, and y equal to t to the power 4 minus 2t squared. Find all points where the tangent line is either horizontal or vertical. We know that when the tangent line is horizontal, the derivative must be 0. And when the tangent line is vertical, the derivative must be either positive or negative infinity. So let's find the derivative first. The derivative of the function is dy over dx, which is dy over dt over dx over dt. Dy over dt here is 4t cubed minus 4t. ds over dt here is 3t squared minus 6t minus 9. Let's simplify first. If I simplify, the numerator can be factored as 4t times t squared minus 1. If I keep factoring, I can write it as 4t times t plus 1 times t minus 1. On the denominator, I can factor 3 out. If I pull out 3, I get t squared minus 2t minus 3. Keep factoring, I get 3 times t minus 3 t plus 1. Cancel t plus 1 from top and the bottom. The derivative of the tangent line can be written as 4t over 3 times t minus 3. That's the derivative of the parametric equations. This is the derivative of the parametric equations. Then, for horizontal tangent line, we set the numerator equal to 0. For vertical tangent line, we set the denominator equal to 0. Because horizontal tangent line occurs when the derivative is 0, and vertical tangent line occurs when the derivative is positive or negative infinity. Solve an equation for t. I get t equal to 0, t equal to 3. That means when t equal to 0, there's a horizontal tangent line. And when t equal to 3, there's a vertical tangent line. Then plugging 0 and 3, we can find a point. If I plug in 0, s is 0. If I plug in 0 for y is also 0. So when t is 0, the point on the curve is 0, 0. If I plug in 3, x is 3 cubed minus 3 times 3 squared minus 9 times 3. That's negative 27. Y is 3 to the power 4 minus 2 times 3 squared. 3 squared is 9. 2 times 9 is 18. 3 to the power 4 is 81. 81 take away 18 is 63. So the point here is negative 27, comma 63. That means at this point, the tangent line on the curve is vertical. Next example, let s equal to e to the power t minus t, and let y equal to 2t to the power 3 minus 6t squared. Find all points when the tension line is either horizontal or vertical. We know that when the derivative is 0, the tension line is horizontal, and when the derivative is positive or negative infinity, the tension line is vertical. So let's find the derivative first. dy over dt is dy over dx is dy over dt over dx over dt. For dy over dt, take the derivative of y with respect to t. I get 6t squared minus 12t. dx over dt, take the derivative for function x with respect to t. I get e to the power t minus 1. Then, for horizontal tension line, we set the numerator to 0. For horizontal tension line, set numerator to 0. For vertical tension line, set denominator equal to 0. Then solve the equations for t. For the numerator here, I can factor 6 out, factor 6t out. I get t minus 2. Solve for t, I get t equal to 0, t equal to 2. Solve the denominator. I have e to the power t equal to 1. Apply Ln to both sides. T equal to Ln of 1. Ln of 1 is 0. That means when t equal to 0 and 2, the tension line is horizontal. When t equal to 0, the tension line is vertical. Do we see a problem here? When t equal to 0, the tension line is horizontal and vertical at the same time. How possible is that? That's impossible. In general, a tension line cannot be horizontal and vertical at the same time. So in this case, what should we do? Here we have 0 over 0. What should we do? So take a limit. For the slope at t equals 0, take a limit. For the slope at t equals 0, take a limit as t approaches to 0. For the derivative, 6t squared minus 12t, e to the power t minus 1. Take derivative from the derivative. Take a limit from the derivative. If the limit is 0, if eventually turn out the limit is 0, that means the tension line is horizontal. If the slope is positive or negative infinity, if the limit is positive or negative infinity, that means the tension line is vertical. If here turn out the limit is neither, it's not 0 and no plus minus infinity, that means the tension line is neither horizontal nor vertical. If the slope is not 0, it's not infinity, that means the tension line is neither horizontal nor vertical. So take a limit here. Here we have 0 over 0. We can apply L'Hopital's rule. If we apply L'Hopital's rule, the limit is 12t minus 12 on the numerator and e to the power t on the denominator. Then plugging 0 again, so the limit t is 0. Plugging 0 again. If I plug in 0, I have 12 times 0 minus 12 over e to the power 0, which is negative 12 over 1. So the answer is neither infinity nor 0. If the slope is neither infinity nor 0, the tension line is neither horizontal nor vertical. So 0 are both rejected. So here the answer t equals 0 is rejected. That means there's a horizontal tension line at t equal to 2. There's a horizontal tension line when t equal to 2. And there's no vertical tension line. There are no vertical tension lines. So for when t equal to 2, the x coordinate is e to the power 2 minus 2. Y coordinate is 2 times 2 cubed minus 6 times 2 squared, which is 16 minus 24, which is negative 8. So the point that has horizontal tension line is e squared minus 2 comma negative 8. That's the point where it has a horizontal tension line. And we know that since t equals 0 is rejected, there are no vertical tension line. So that's the only solution to this problem. Next, let me introduce the second derivative of parametric equations. Assume all functions are continuous and differentiable. How do we find the second derivative? D squared y over dx squared. We know that the second derivative is the derivative of the first derivative. How do we take derivative for this? Here, let's make substitution. Let u equal to dy over dx. Let's make one substitution. Let u equal to what? Let u equal to dy over dx. Then this expression can be written as d dx of u. That's the same as du over dx. Then du over dx can be written as du over dt over dx over dt. Since u equal to dy over dx is a function of t, so u is also a function of t. So du over dx, if I take derivative, that's du over dt over ds over dt. Then on the numerator, du over dt is the derivative of u with respect to t. Denominator is ds over dt. The numerator, derivative of u with respect to t. U is dy over dx. Let's substitute back. U is dy over dx. Denominator stays the same. So that's the second derivative. So the formula for second derivative is d squared y over dx squared equal to derivative of the derivative with respect to t. Derivative of the first derivative with respect to t over dx over dt. That's the formula for the second derivative. That's the formula for the second derivative of parametric equations. Of course, assume the denominator is not zero. Now, be very, very careful. Let me tell you some common mistake. The second derivative is not the second derivative of y over the second derivative of x with respect to t. That's one common mistake. Another common mistake, the second derivative is not the derivative of the first derivative with respect to t. Those are two common mistakes. Be very, very careful. This is the correct formula for the second derivative. Assuming the denominator is not zero. That's the correct formula for the second derivative. Next, let me show you an example about the second derivative. Let s equal to 2 sine t and y equal to 3 cosine t. Find the second derivative, d squared y over dx squared. In order to find the second derivative, let's find the first derivative first. dy over dx is dy over dt over dx over dt. dy over dt is negative 3 sine t. ds over dt is 2 cosine t, which can be rewritten as negative 3 over 2 tangent t. Sine t over cosine t is tangent t. Next, let's compute the derivative of the first derivative with respect to t. Let's compute the derivative of this derivative with respect to t. If I take this derivative with respect to t, derivative of tangent t is secant squared t. So I got negative 3 over 2 secant squared t. Then for the second derivative, d squared y over dx squared, the formula is the derivative of the first derivative over dx over dt. The derivative of the first derivative is negative 3 over 2 secant squared t over ds over dt. ds over dt is 2 cosine t. Here I can try to write secant in terms of cosine. secant square t can be written as 1 over cosine square t. In the denominator, 2 cosine t can be written as 2 cosine t over 1. When we divide two fractions, I can flip the bottom over. That's negative 3 over 2 times 1 over cosine square t times 1 over 2 cosine 1 over 2 cosine t. Multiply together, that's negative 3 over 4 cosine cube t. That's the second derivative. Next example, let s equal to t cubed plus 3t, and let y equal to t squared minus 3. For which value of t is a parametric curve concave up, and for which value of t is a parametric curve concave down? We know that when the second derivative of a function is positive, the graph of the function is concave up. And when the second derivative is negative, the graph is concave down. So in order to test for concavity, we need to find the second derivative. Let's find the first derivative first. dy over dx is dy over dt over dx over dt. dy over dt is 2t. ds over dt is 3t squared plus 3. Then we find the derivative of the first derivative with respect to t. Find the derivative of the first derivative with respect to t. Here we use quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom over the bottom square. Simplify. On the top we have 6t squared plus 6 minus 12t squared over, let's leave the bottom the same, 3t squared plus 3 squared. On the top, if I combine like terms, I get 6 minus 6t squared over 3t squared plus 3 squared. Then we know that the second derivative d squared y over dx squared is d dt of dy over dx over dx over dt. ddt of dy over dx is 6 minus 6t squared over 3t squared plus 3 squared, and ds over dt is 3t squared plus 3. We can write the denominator over 1. Then when we divide fraction by fraction, we flip the bottom fraction over. We get 6 minus 6t squared over 3t squared plus 3 squared times 1 over 3t squared plus 3. Then multiply. The second derivative can be written as 6 minus 6t squared over 3t squared plus 3 squared plus 3 cubed. Then we need to find the critical point of the second derivative. For critical points, we set both the numerator equal to 0 and denominator equal to 0. All solutions are critical points. So I set 6 minus 6t squared equal to 0 on the top. On the bottom, I set 3t squared plus 3 cubed equal to 0. Solve for t. So we have t squared equal to 6 over 6, which is 1. T equal to plus or minus 1. If I solve this equation, I get, take cube rule on both sides. I get 3t squared plus 3 equal to 0. T squared equal to negative 1. We know perfect square cannot be negative 1, so there are no solution here. That means the only critical point is positive 1 and negative 1. The only critical point here is positive and negative 1. Then let's apply a number line test. put -1 and +1 on the number line. Test for positive and negative values. Let's test for positive negative value for the second derivative. Let's pick some test number for t. We pick test number less than -1, which could be -2. Pick test number between -1 and 1, which could be 0. Pick test number greater than 1. I can pick 2. Plug each test number into the second derivative. Plug in here. If I plug in -2 here, -2 squared is 4. 6 times 4 is 24. 6 minus 24 is negative on the numerator. If I plug in -2 to the denominator here, denominator square is 4. -2 squared is 4. 3 times 4 is 12. 12 plus 3 is 15. 15 cubed is positive. Negative number over positive number is negative. So the second derivative is negative here. Then I plug in 0. Plug in 0 for t. If I plug in 0, the numerator is 6, which is positive. If I plug in 0 to the denominator is 27, which is also positive. Positive number over positive number is positive. So when t is 0, the second derivative is positive. Then I plug in 2. If I plug in 2 to the numerator, 6 minus 24 is negative. If I plug in 2 to the denominator, I get 15 cubed, which is positive. Negative number over positive number is negative. So when t is 2, the second derivative is negative. When the second derivative is negative, the curve is concave down. When the second derivative is positive, the curve is concave up. When the second derivative is negative, the curve is concave down. So when t is less than -1 or t is greater than 1, the parametric equation, the parametric curve is concave down. When t is between -1 and 1, the parametric curve is concave up. Next, I'll show you how to find area under a parametric curve. First of all, let me review an old formula about areas under the curve. Area under a curve y equal to f of x from x equal to a to x equal to b is area equal to the integral x from a to b f of x dx. That's the old formula we learned in first semester calculus, which represent the area under the curve y equal to f of x. X varies from a to b. That's the old formula we learned in first semester calculus class. Now, for the new formula about parametric equations, I can first of all replace f of x with y. Then, since we consider x and y are parametric equations with parameters t, I can take integral when t varies from a to b. This formula represents area between the parametric curve and the x-axis. For t is between a and b. For t varies from a to b. Now similarly, for area between the parametric curve and the y-axis, the formula is very similar. For area between the parametric curve and y-axis, the formula is very similar. T varies from a to b. Instead of y dx, we have x dy. That represents area between the parametric curve and the y-axis. When t is between a and b, when t varies from a to b. Now, when we use this formula to compute areas, we need to be very, very careful with one thing. Note, if an area is above x-axis, if an area is above x-axis, when we take integral from left to right, this area is positive. When the area is under curve, under the x-axis, when the area is under x-axis, when we take integral from left to right, this area is negative. That's for area between the curve and the x-axis. Now for the area between the curve and the y-axis, when the area is in the right side of the y-axis, when the area is in the right side of the y-axis, this is positive area. And we'll integrate from bottom to top. We'll integrate from bottom to top. If the area is in the right side of the curve, of the y-axis, this is positive area. We'll integrate from bottom to top. If the area is in the right side of the y-axis, we'll integrate from bottom to top. If the area is in the right side of the y-axis, this area is negative area. Next, let's look at an example about areas. Let s equal to 6t minus t squared plus 5, and y equal to 3t plus 5. Find the area between the parametric curve and the x-axis when t is between 0 and 2. Part B, find the area between the parametric curve and the y-axis when t is between 0 and 2. So for part A, we're looking for area between the parametric curve and the x-axis. We use the formula integral of y dx, t from A to B. Now here in this problem, function y is 3t plus 5. What's dx? Since x is 6t minus t squared plus 5, dx will be 6 minus 2t times dt. That's dx. Dx is 6 minus 2t times dt, and t varies from 0 to 2. Then take an integral. Let's FOIL first. I get 18t minus 6t squared plus 30 minus 10t dt. Combine like terms. I have 8t minus 6t squared plus 30 dt. Then take antiderivative with respect to t. I get 4t squared minus 2t cubed plus 30t. Evaluate from 0 to 2. If I plug in 2, 2 squared is 4, 4 times 4 is 16. 2 cubed is 8, 8 times 2 is 16. 30 times 2 is 60. If I plug in 0, I get 0. So the answer is 60. That means the area between the parametric curve and the x-axis is 60. Area between the parametric curve and x-axis from when t is from 0 to 2, area is 60. Now for part B, find the area between the parametric curve and the y-axis. Here we use the formula a equal to integral of x dy when t is from a to b. Here function x is 6t minus t squared plus 5. That's function x. What's dy? Since y is 3t plus 5, dy is 3 dt. So dy is 3 times dt. And t is from 0 to 2. Then take integral. First of all, distribute 3. I get 18t minus 3t squared plus 15 dt. Then take antiderivative with respect to t. I get 9t squared minus t cubed plus 15. Then evaluate from 0 to 2 plus 15t. Evaluate from 0 to 2. If I plug in 2, 2 squared is 4. 4 times 9 is 36. If I plug in 2 here, 2 cubed is 8. If I plug in 2 here, 15 times 2 is 30. Then if I plug in 0, I get 0. 36 minus 8 is 48, is 28. 28 plus 30 is 58. So that's an area between the curve and the y-axis when t is from 0 to 2. Next example, let s equal to 2 cosine t and y equal to 2 sine t, but an area enclosed by the parametric curve. What does it mean, area enclosed by the parametric curve? Let's sketch a parametric curve first. How does a parametric curve look like? We can plot some points. Plot some point for t, x, and y. For trig functions, we plot t values for 0, pi over 2, pi, 3 pi over 2, and 2 pi. When t is 0, the point is 2, 0. When t is pi over 2, the point is 0, 2. When t is pi, the point is negative 2, 0. When t is 3 pi over 2, the point is 0, negative 2. When t is 2 pi, the point is 2, 0. So the graph looks like this. When t is 0, the point is 2, 0. When t is pi over 2, the point is 0, 2. When t is pi, the point is negative 2, 0. When t is 3 pi over 2, the point is 0, negative 2. When t is 2 pi, it goes back to 2, 0. Then if we connect these points, the graph looks like a circle. The graph looks like a circle. And as t increases, it goes this way, counterclockwise. It goes counterclockwise. As t increases, it moves counterclockwise. Let's verify. If x equal to 2 cosine t, that means cosine t is x over 2. If y equal to 2 sine t, that means sine t is y over 2. Cosine square t is x squared over 4. Sine square t is y squared over 4. We know that cosine squared plus sine squared is 1. So x squared plus 4 plus y squared over 4 is 1. Multiply both sides by 4. We have x squared plus y squared equal to 4. That's a circle of radius 2. That's a circle center and origin with radius 2. So that's this circle. Now find an area enclosed by the parametric curve. So here, for one cycle, t varies from 0 to 2 pi. So t varies from 0 to 2 pi. For one cycle, t varies from 0 to 2 pi. We can use the area between the curve and x-axis, and the area between the curve and the y-axis is the same. There's no big difference. For the area between the curve and x-axis and the area between the curve and the y-axis, there's no difference. So let's use y dx. Let's use y dx. Y is 2 sine t. What's dx? X is cosine t. That means dx is negative sine t dt. So sorry, x is 2 cosine t. So dx is negative 2 sine t dt. Then plug in. Dx is negative 2 sine t dt. Let's take integral here. I can first of all pull out 2 and negative 2, which is negative 4. Sine t times sine t is sine squared t. Next, we can use half angle identity for sine squared of t, which is half of 1 minus cosine 2t dt. Negative 4 times half is negative 2. Then take antiderivative with respect to t. Antiderivative of 1 is t. Antiderivative of cosine 2t is half of sine 2t. Evaluate from 0 to 2 pi. If we plug in 2 pi, we have 2 pi minus sine of 2t. If I plug in 2 pi here, I get sine of 4t. Sine of 4t is 0. If I plug in 0, everything is 0. So the answer is negative 4 pi. So the area enclosed by this circle is negative 4 pi. Does this answer make sense? Can area enclosed by a circle be negative? Now let me explain why we are getting negative area here. This integral for t from 0 to 2 pi, y dx can be written as integral from 0 to pi y dx plus integral from pi to 2 pi y dx. Integral from 0 to pi y dx represent the area between the curve and x-axis when t is from 0 to pi. 0 is here, pi is here. So integrate from right to left. When we integrate from right to left, this becomes a negative value. For positive value, we must integrate from left to right. So when we go from right to left, this integral gives a negative value. Now for the second integral, from pi to 2 pi, from pi to 2 pi, pi is here, 2 pi is here. That's the lower half of the circle. Here we integrate from left to right. However, this area is under a curve, so it's negative area. This area is under curve, it's negative area. So this is also a negative value. Since we get negative value for both integrals, that's why the answer is negative. So the correct way to take integral for this problem, the correct way to take integral is we first of all need to integrate from left to right. So for the upper half, take integral from pi to 0. For the upper half of the circle, take integral from pi to 0. Y dx. That's an area, that's an upper half circle. That's an area of an upper half circle. Now for the lower half, since it's negative, since from pi to 2 pi is negative value, we need to change the sign. Negative integral from pi to 2 pi, y dx. Then plug in. This answer should be positive. This answer should be positive. From pi to 0, y is 2 sine t. Dx is negative 2 sine t dt. The other integral, plus minus become minus. Integral from pi to 2 pi, y is 2 sine t. Dx is negative 2 sine t dt. Take this integral, answer should be positive. So apply the same procedure. The antiderivative for this integral is t minus negative 2 times t minus half of sine 2t. So the antiderivative should be negative 2 times t minus half sine 2t. Evaluate from pi to 0. For the other part, antiderivative is the same. Negative 2 times t minus half sine 2t. Evaluate from pi to 2 pi. If I plug in 0, I get 0. If I plug in pi, I get pi minus 0. For the second half, double negative is positive. If I plug in 2 pi, I get 2 pi. Sine 4 pi is 0. If I plug in pi, I get pi. Sine 2 pi is 0. Together, I get 2 pi plus 2 pi, which is 4 pi. That's the actual area under enclosed by the parametric curve. That's the area enclosed by the parametric curve. And this answer is wrong. That's a correct solution. Next, we'll study arc-length formulas for parametric curves. Let me first of all review an old formula. An old formula says the arc length of a curve the arc length of the curve y equal to f of x from s equal to a to s equal to b is the length of the arc is x from a to b square root of 1 plus dy over dx square dx. That's the old formula. Next, I'll try to derive a new formula from here. If we consider x and y are parametric equations with perimeter t, then x is a function of t. Dx can be written as x prime of t dt. That means dx is dx over dt times dt. X prime of t can be written as ds over dt. Then this arc length formula, the last part, ds can be written as ds over dt dt. Now for the integral, for the square root here, since we consider x and y are parametric equations, so the derivative of dy over dx can be written as dy over dt over dx over dt square. Now for the integral, since the variable is t, we take t values from a to b. Take integral when t values from a to b, since the variable here is t. Since both s and y are functions of t, so the variable is t. So we take integral when t values from a to b. Then let's multiply everything out. If I multiply ds over dt into the square root, it becomes dx over dt square. Leave dt outside. Then distribute ds over dt square. One times ds over dt square is ds over dt square. If I multiply ds over dt squared to the second term, it cancels the denominator. What's left is dy over dt square dt. So that's the new arc length formula. That's an arc length formula for parametric curves. That's an arc length formula for parametric curves. Now let's look at an example here. Let s equal to t squared plus 4 and y equal to 4t cubed minus 2. Find the length of an arc when t is from -1 to 0. Here we are looking for arc length. So we can use an arc length formula. T from A to B square root of dx over dt squared plus dy over dt squared times dt. Since x is t squared plus 4, ds over dt is 2t. Since y is 4t cubed minus 2, dy over dt is 12t squared. Then we can plug in. If we plug in, t is from -1 to 0. We have square root of 2t squared plus 12t squared square dt. Simplify the integral. We have square root of 4t squared plus 12 squared is 144. T squared is t to the power 4 dt. Then here I can factor, I can pull out 4t squared. If I pull out 4t squared, I have 1 plus 36t squared dt. Then we know that square root of 4t squared is 2t. 2t times 1 plus 36t squared times dt. Then we can make u substitution here. The u will be 1 plus 36t squared. Then the u will be 72t dt. We have 2t here, so the integral is 1 over 36 square root of u du. When we plug in 0 for t, 1 plus 36 times 0 squared is 1. When we plug in -1 for t, -1 squared is 1. 1 plus 36 times 1 is 37. That's the new integral. Then I can pull out 1 over 36. Square root of u can be rewritten as u raised to a half du. Then take antiderivative. Antiderivative of u to a half is u raised to 3 over 2 over 3 over 2. Evaluate from 37 to 1. Simplify the answer, we get 1 over 36 times 2/3. If I plug in 1, I get 1. 1 raised to 3 half is 1. If I plug in 37, 37 raised to 3 half is 37 square root of 37. So the answer is 1 over 54 times 1 minus 37 over 37 times radical 37. This answer here, 1 minus 37 times radical 37, this is a negative number. Can arc length be negative? Can arc length be negative? Arc length is always positive, it can never be negative. Then what's the mistake here? Arc length won't be negative. What's the mistake here? Here, be very, very careful. Let me remind you one thing. If x is greater or equal to 0, then square root of x squared is x. What if x is negative? If x is less than 0, then square root of x squared is negative x. Be very, very careful. Square root of x is not always x. If x is less than 0, square root of x squared is negative x. Now here, when t varies from -1 to 0, t is negative. So 4t squared here, 4t squared must be negative 2t. Because when t varies from -1 to 0, t is negative. So square root of t squared must be negative t. Square root of 4 is 2. So the answer is negative 2t here. So the sign varies. The sign changes here. So this integral becomes negative. The sign changes everywhere. So eventually, the final answer, 1 over 54 times 37 times radical 37 minus 1. That's the final answer. Next example, let s equal to 3 cosine t, y equal to 3 sine t. Find the length of an arc when t is between 0 and 2 pi. So here apply arc length formula. T is from A to B. Square root of dx over dt squared plus dy over dt squared times dt. Here x is 3 cosine t. So ds over dt is negative 3 sine t. Y is 3 sine t. So dy over dt is 3 cosine t. Then plug in. T varies from 0 to 2 pi. ds over dt is negative 3 sine t squared. dy over dt is 3 cosine t squared. Simplify. Negative 3 sine t squared is 9 sine squared t. 3 cosine t squared is 9 cosine squared t dt. Here I can pull out 9. If I pull out 9, I have square root of sine t squared plus cosine t squared dt. Square root of 9 is 3. Sine square of t plus cosine square of t is 1. Square root of 1 is 1. So I get 3 times 1 times dt. Then take antiderivative for number 3 with respect to t. I get 3t. Evaluate from 0 to 2 pi. If I plug in 2 pi, 3 times 2 pi is 6 pi. So the length of the arc is 6 pi. That's an answer. Next example. Let s equal to e to the power of negative t cosine t and y equal to e to the power of negative t sine t. Find the length of an arc when t is between 0 and pi over 2. So here we apply arc length formula. T is from A to B. Square root of ds over dt squared plus dy over dt squared times dt. Here x is e to the power of negative t cosine times cosine t. So for ds over dt here, we use product rule. Derivative of the first times the second plus the first times derivative of the second. That's negative e to the power of negative t times cosine t plus sine t. Y is e to the power of negative t times sine t. For dy over dt, we use product rule here. Derivative of the first times the second plus the first times derivative of the second. That can be written as negative e to the power of negative t sine t minus cosine t. Then plug into the formula. Here t varies from 0 to pi over 2. We have square root of negative e to the power of negative t cosine t plus sine t squared. Dy over dt is this. Negative e to the power of negative t sine t minus cosine t squared times dt. Then multiply out. I have e to the power of negative 2t times, expand perfect square here, I get cosine square plus 2 cosine t sine t plus sine square t plus e to the power of negative 2t sine square t minus 2 sine t cosine t plus cosine square t, then times dt. Then pull out e to the power of negative 2t. I get square root of e to the power of negative 2t. Pull out e to the power of negative 2t. I have cosine square of t plus cosine square of t. It's 2 cosine square of t. 2 cosine t sine t cancels negative 2 sine t cosine t. Sine square of t plus sine square of t is 2 sine square of t times dt. Square root of e raised to negative 2t. Square root of e raised to negative 2t is e raised to negative t. If I factor 2 out, I get square root of 2 times square root of cosine square of t plus sine square of t dt. This is 1. Cosine square of t plus sine square of t is 1. This is 1. And square root of 2 is a constant. I can put it outside. Integral from 0 to pi over 2 e raised to negative t dt. Then I take antiderivative. I get negative e raised to negative t. T varies from 0 to pi over 2. Then, if I plug in 0, e to the power of 0 is 1. If I plug in pi over 2, I get negative 1 minus negative e to the power of pi over 2. That can be rewritten as square root of 2 times e to the power of pi over 2 minus 1. That's the final answer.